Stars that are higher than that also achieve the temperature to burn carbon in an ideal gas, and that leaves an oxygen white dwarf. The temperature for that would be around 600 million Kelvin. So the structure of a star like that would have an inert oxygen core, a carbon burning shell, a helium burning shell, and then a hydrogen burning shell, and then a non-burning hydrogen envelope. Now, for even higher temperatures, carbon is burned as an ideal gas. Carbon burns into oxygen by capturing alpha particles. And then once carbon is exhausted, oxygen burns into neon. Because this is a series of alpha particle captures, we call this as climbing the alpha ladder. Low mass stars produce elements up to carbon and oxygen, but high mass stars produce all of the rest of the periodic table. Up to iron, basically what you have is a series of alpha reactions. Carbon captures a helium particle, produces oxygen. Oxygen captures a helium particle, produces neon. Neon produces magnesium, and it goes on and on. Now, other reactions are carbon fusing with oxygen to produce silicon, or oxygen and oxygen to produce sulfur, or silicon and silicon to produce iron. Now, notice why it's capture of helium particles that is happening. Capturing an alpha particle is preferred than capturing a proton, because when you look at the nuclide charts, so this is the number of protons, this is the number of neutrons. If you add only protons, you are climbing here to this side, to the left-leaning side of the plot, and you enter a region where the nuclides are unstable to positron emission, means that the proton is decaying. We call this inverse beta decay, because the beta decay is when a neutron decay and emits an electron and the proton stays in the nucleus. But if you add a helium nucleus, if you add an alpha particle, you're adding the same number of protons and neutrons. So you are going along the valley of beta stability, where no beta decay and no inverse beta decay happens. That's the green part here of the nuclide chart.